Good afternoon, ladies and gentlemen, and welcome to this afternoon's session on upgrading traditional buildings. Just to give a bit of background, there's not an insignificant number of traditional buildings around the country, estimates up to maybe 250,000 buildings that come under the heading of traditional buildings. And currently, they're not really provided for by the SEAI grants, and that's an issue. And we need to be able to facilitate or support the upgrade of all buildings in the country. There are some stumbling blocks and there are some new guidelines being issued by the Department of Housing that are being worked on at the minute and should come out later this year. And as part of that, we've been engaging with all the right people in terms of what we can do and how we can get this right, because it's really important. They're really difficult buildings to do in some cases, and it's important that all the pieces of the jigsaw are right and are put together and have the right people working on them. I'm not going to take any longer time. You don't want to hear from me. So I'm going to introduce our three speakers first. I'm going to have to read them because they're far too accomplished for me to memorise them. So first up, we have Jackie Donnelly from the Department of Housing. Jackie is the Senior Architect in Built Heritage Policy at the Department of Housing, Local Government and Heritage, and is Grade 1 accredited Conservation Architect with the RIAI. She's engaged in the implementation of the Climate Change Sectoral Adaptation Plan for Built and Architectural Heritage, and chairs an interdepartmental committee overseeing the preparation of new guidance document improving the energy efficiency of traditional buildings, which she's going to be presenting to us on, and which is due for publication later this year. She's also a member of the ICOMOS International Scientific Committee on Energy and Sustainability and was a founding steering committee member of the International Climate Heritage Network. So what Jackie's going to be talking about today is these new guidelines on upgrading traditional buildings and how they're very different to the modern buildings that we're used to built in the last 50, 60 years. And that you can do real damage to a house if you do what you might think would be the right things that we do to more modern houses. But if you apply those same solutions to traditional buildings, you can do some serious damage to the structure. So it's important we differentiate them and have the right guidelines in place. And looking at it as well is not just energy conservation as being the primary thing, but building conservation, that we retain our buildings, retain their character, and do the right things rather than just knocking old buildings to build the same thing back in their place. Because it's got a real issue, a real impact on embodied carbon use as well. So next up we have Dr. Oliver Canaan, who is an academic lead of the Building in a Climate Emergency Research Group at the School of Architecture, Planning and Environmental Policy in UCD. He's the founder and director of the MSc in Architecture, Urbanism and Climate Action. His research is focused on building construction, conservation and operation, and improving the performance of the built environment. He has 4 SEAI RD&D projects, so Fab Trads, which we'll be hearing about today, which looks at the hydrothermal testing of traditional building fabrics, Macaire H, which is evaluating heat pump performance and use, Kugi, you might correct that if I'm wrong, which is investigating models of compact urban growth, and NZEB 101, analysing the performance of NZEB buildings. He's also has EPA Construct, Innovate and Horizon 2020 funding, and is leading the whole life carbon in Irish construction sector and built environment study with Dr. Richard O'Haggerty for the Irish Green Building Council. So again, like I said, he's going to talk about the Fab Trads project, which is looking at the thermal hydrothermal performance of traditional building fabrics. And lastly, we have Joseph Little, who's the Head of Construction and Building Performance in the School of Architecture and Built Environment in TU Dublin. He holds an MSc in Architecture, Advanced Environmental and Energy Studies from the Graduate School of the Environment Centre for Alternative Technology in Wales, and a Bachelor of Architecture and Professional Diploma from UCD. He's a Director and founding member of the IGBC. He's also Programme Chair of the MSc in Building Performance, Energy Efficiency and Design, and BSc in Sustainable Timber Technology. His area of research is hydrothermal risk evaluation, low carbon, circular construction, and energy efficient renovation. His passion is to support a fundamental shift towards a high quality, low impact and sustainable built environment. So today, Joseph is going to take you through a whistle-stop tour of a deep retrofit of his own traditional building, and looking not just at the materials we use and the embodied carbon, but also building in the circular economy, the circularity of materials and reusing materials as a product rather than just being something that you use at a very base level. So I want to invite up Jackie Donnelly from the Department of Housing first to be our first speaker.
Great, thank you very much, Brian. So we're going to talk to you about just issues around traditional buildings and upgrading them based on the guidance that we're hoping to produce later this year. Okay. So what is a traditional building? We've defined it as buildings that are built with solid masonry walls, so maybe masonry, brick or stone, often with a rendered finish, so they're not cavity walls. They were usually built with single glazed timber or metal framed windows, timber framed roofs as well, slate or tile coverings, sometimes thatch or metal. And they're flexible and of what we call breathable construction, generally built with no damp-proof courses as well. And this was the type of construction that was used in Ireland for the majority of buildings built before, say, 1940. And it could be between 15 and 18% of the existing building stock. And it covers a very wide range of buildings. I mean, you can see everything from medieval tower houses, vernacular mud-walled houses, country houses, urban terraced houses from the Georgian period, the Victorian periods, commercial premises. These are the kind of buildings that make up the centres and cores of our historic towns and villages. As well, industrial buildings, places of worship are all covered by this. So they're an extensive type of building type. So the kind of methods that are used to make traditional buildings evolved over the centuries. And they used local materials and local craft skills. And they knew how to deal, by trial and error, with what the local weather conditions were and how best to provide shelter. And the main difference between traditional construction and modern construction is really how moisture is managed within the building fabric. These building materials are usually soft and flexible and vapor permeable. And as I said, need to be breathable, so need to be able to absorb moisture from the atmosphere when the weather is wet and then be able to release it out when conditions are improved without the moisture having penetrated right into the middle of the, into the interior of the building. And there was a lot of natural ventilation in these buildings through open fireplaces, maybe gaps between the meeting rails of sash windows, around windows and doors. But it's important to note these buildings weren't built to be drafty. They may have become drafty over the years because buildings have settled, because joints may have opened in windows and doors, or but people didn't build these buildings to be uncomfortable. They were built to the standards of the day and to provide comfort for the inhabitants. So it's important to stress that these traditional buildings and the works that need to be different to them is irregardless of statutory protection. So we're not just talking about protected structures, buildings and architectural conservation areas. We are really talking about how these buildings were constructed and the building physics in which they operate. So it's essential to understand how these buildings work before you specify or carry out works to them to avoid causing irreversible damage. And it's important also to remember that the elements in a traditional building aren't isolated and separated by barriers and cavities as they might be in modern construction. So the building needs to be looked at as a whole. And we need to balance the requirements of energy conservation and then of building conservation too, protecting their architectural heritage and their character. So we produced a book, I've just got one copy of it here, back in 2010, just to advise owners on what they needed to bear in mind when they were commissioning works to their buildings to upgrade them. They included a couple of small drawings just to show the differences between modern construction and traditional construction. And it's been compared to the difference between a raincoat and a greatcoat. Though I don't think the term greatcoat is used that often anymore. But like a raincoat is all about repelling moisture from the building, making sure nothing gets inside. So modern construction has dense, hard renders on the outside. They have deep foundations to make sure that the building doesn't flex at all. They have damp-proof membranes under the floor. They have damp-proof courses within the walls. And then you have to provide ventilation, trickle ventilation through the windows maybe, or, extractor fans and the like. Whereas traditional construction accepted the fact that they were going to absorb moisture, that it was going to come up through the floors and dissipate into the house, that, as I said before, going to come in through the walls, but not penetrate the whole thickness of the walls. Before then, they were allowed to dry out. There was a certain amount of kind of gratuitous ventilation provided through, as I said, maybe meeting styles of windows, gaps between slates and open fireplaces as well. So there are risks associated with a building, altering a building that has been giving good service for 150, 200, maybe even more years. And Therefore, we would claim that the specification of retrofitting works should generally only be undertaken by those that are competent and have the necessary skills and experience and know what they are dealing with and what are the likely outcomes. Where a project is particularly complex or the building is of high architectural heritage significance, there's yet another kind of particular skill set that will be required of the specifier and the installer. But there are certain low-risk interventions, that a good, skilled and experienced contractor or craftsman can do, particularly where the building isn't protected. There are several different types of statutory and regulatory requirements that you need to be aware of. There are a lot of actual, believe it or not, living, working buildings that are protected under the National Monuments Acts because maybe they have some medieval or early fabric in them. But the majority of the architectural heritage of this country is protected under the Planning and Development Acts, where buildings can be protected structures, they can be located in architectural conservation areas, and then there may be other buildings that are protected in various other ways. Building Control Acts and regulations then is another thing to bear in consideration, and it's important to note that buildings protected under the National Monuments Acts are exempt from having to comply with the building regulations. Building energy rating then coming out of that. There are a number of exemptions for the requirements for BER and for compliance with TGDL of the building regulations, and that includes protected structures, buildings used as places of worship or for religious activities, and again, buildings protected under the Monuments Acts. So a lot of those will be of traditional construction. But that's not to say that people won't want to upgrade the energy performance of these buildings, and it is possible, but just to know they don't have to chase the particular legislative requirements. Important before you start doing any works or even considering them, that you understand your building, approximately when it was built, what its architectural heritage significance is, what the kind of construction methods and materials that were used, and then what kind of alterations or interventions may have taken place later, and are they appropriate or not? There may have been interventions such as, a lime render may have been removed and replaced with a cement render, and maybe that should be undone now to allow, restore the vapour permeability of the wall. And then important to look at the condition of the building as a whole. Because before any retrofitting works begin, it is really important that your building is in good repair and it's dry, because a damp wall transmits heat at a higher rate than a dry one will. And, to the extent of 20 to 30%, maybe energy efficiency improvements could be made just by having a dry wall. Now, it can be a long process to dry out a masonry wall that could be, 800 millimetres thick if it's a medieval wall, or even larger. Also look at your building and see, are there any energy efficiency design features in the building and how you could use and upgrade those. Many buildings, particularly from the Georgian, Victorian, so the 18th, 19th centuries, would have had timber shutters, and they can be upgraded and they can provide very good energy efficiency as well when they're closed. Again, any inappropriate later changes, try to reverse them where it can be done without damage. Many times it can be very difficult and very damaging and expensive to try and remove things like Portland cement from pointing or from render and the like. So that will need to be carefully assessed as to whether it's worth doing or not. Obviously, identify and remove or contain any toxic materials in the building. And it can also be very useful to try and get an assessment of what the building's energy usage was before the works were carried out, so you can compare that to what you're getting at a later stage after the retrofitting works. You need to pay careful attention to ventilation and the indoor air quality in these kind of buildings. Air tightness, ventilation, indoor air quality, they're all interdependent, and any retrofit plan needs to address all these together, because good ventilation is critical to the well-being of most traditional buildings. Because if you get high moisture content within timbers in your building, or you could get, you will actually make things like timber joists, timber rafters and the like very vulnerable to rot and insect infestation as well. And also you need to be very careful that you don't trigger any interstitial condensation. So condensation that actually happens within the depth of a wall, and that can be very damaging because it's invisible. And as we've all learned over the last few years, people too require proper ventilated living spaces for their health and their comfort. But just to say a word about sustainability in historic buildings, because many times we're faced with people who say, you know, oh, the best thing you do is knock it down, build a new, you know, A-rated house. But actually, the greenest building, as has been said, is the one that's already built. It is there, it has already paid off its carbon footprint by lasting for hundreds of years. And the continued use and reuse of our older buildings is going to be extremely critical going forward to avoid greenhouse gas emissions. Because too often, up till this, carbon reduction strategies for the built environment have really concentrated on the operational emissions, so the amount of energy that goes into heating, lighting and using a building and the performance of the fabric, rather than looking at the carbon issues as well. And you know, we really do have to take account of the carbon emissions when we're looking at our buildings, because that's what counts, is how much greenhouse gas is going into the atmosphere. So we're looking at life cycle analysis as well to assess the sustainability of new buildings versus maintaining, refurbishing or replacing existing buildings. Because we have to bear in mind that if we demolish a building, we lose all the embodied energy in it, we lose most of the materials in it. That all has to be carted off, put in landfill. And then we have to also bring into account the production, the importation, bringing to site and the construction of a new replacement building and the kind of emissions that that entails. And studies have been done. We're commissioning a study here as well. But studies have been done that shows it takes decades to replace, you know, a standard size, you know, two-storey building with an A-rated, you know, traditional building with an A-rated modern construction. So, you know, we don't have that kind of time anymore to get the emissions under control. And then to say, you know, that our older buildings were designed to maximise natural sources of heating, lighting and ventilation. Energy, when these buildings was built, energy was expensive compared to people's incomes. It was really only in the second half of the 20th century, you know, that fossil fuels became very cheap and, you know, central heating and the like became standard in housing. But older buildings were actually built to try and contain the heat, to provide comfortable living conditions. And our building stock is also made of very durable, long-lasting materials that have, you know, reduced refurbishment cycles, and therefore in the long term and over their lifespan they will use less energy. And generally their kind of building elements are very easy to repair. Things like, you know, it's easy to repair joinery, to take out a rotten piece of a window and to replace it with just a single piece, or to repair ironwork as well. So we produced guidance when all the architectural heritage protection legislation first came into force. These guidelines, they were originally for planning authorities to tell them all about their new roles under the Planning and Development Act. But these are the principles of conservation that are, you know, internationally accepted and agreed to. And these, we just re-explain them in an Irish context. So not in any particular order. It's about keeping the building in use, giving it a viable and economic use and value to its owners, recording and analysing the building itself, using expert conservation advice to make sure that any changes you make will not be detrimental to the building, protecting what is special about it in the first place, minimal intervention, you know, trying to do as much as is necessary and as little as possible is what the Borough Charter says, replacing rather than repairing, using the right materials and the right methods, and then making sure wherever possible that things can be reversed. And I think this is particularly the case with retrofitting, that so that if something goes wrong and it's shown not to be working and it's damaging the building, that it is possible to take it out without having caused irreversible damage to the building. And then avoiding incremental damage by small changes that on their own mightn't seem too bad, but cumulatively they can really damage the character of a building. But a lot of these also, as I say, fit into the kind of principles we should have for retrofitting. So good maintenance, as I said, keeping the building dry and in good repair, using materials that are compatible, so, you know, the correct materials, ones that are vapor permeable, capillary active when you're using mortars and the like, making sure that there is adequate ventilation for the health of both the building and its occupants, minimising waste, so wherever you can, upgrading, repairing existing elements rather than throwing them out and replacing them, and balancing the need to conserve the energy with minimising the impacts on the character of the building and its historic fabric. And really, it's all about not pushing the building beyond what it can reasonably achieve. So to get onto the guidance that we're going to publish later this year, it builds on this document that we produced in 2010, which was for owners, but this one is going to be aimed at, the professional user, the specifiers, the installers of retrofitting works. But we do hope they'll be readable and understandable by a wider audience. So it's going to be more strategic than prescriptive. It's very hard to have standard constructional details or standard retrofitting details for historic buildings, because almost all these buildings are different. Even if they were built at the same time, they'll have evolved differently. There'll have been changes to them over the course of their lifespan. So we're going to illustrate good practice and establish the principles and processes to be followed. And it's going to be titled Improving Energy Efficiency in Traditional Buildings. So just to give you a brief idea of what's going to be in it, Chapter 1 is going to explain what we are calling traditional buildings and the kind of buildings will be covered by the guidance, the statutory regulations that apply when you're altering a traditional building, issues to do with the building energy rating system and its application to traditional buildings. There are issues about BER and how it rates traditional building fabric, which you're going to hear more about later. They're often very much underrated in how they perform, their thermal performance. And that leads to problems then that people may overspecify retrofitting works that the building actually doesn't need, and then you don't see the savings you were expecting because actually your building was performing much better in the first place before the work started. We talk about the professional skills and services that might be required. Information then on the full environmental, we're really only touching on this, but take into account the full environmental impact of construction and the embodied carbon and other greenhouse gas emissions. And then information on using building renovation passports to do step-by-step retrofits and make sure you don't get locked in by early decisions that might preclude later, better upgrading measures. Chapter 2 will talk about understanding them, the physics of traditional buildings and how they work and how moisture moves through the fabric, how you might assess the building then to determine are there any thermal bridges, air leakage, or any existing damage to the building, how calculation values for calculating U values for traditional buildings, and then the kind of risks there might be associated with retrofitting, like indoor air quality issues mentioned before, the build-up of harmful substances and gases, and how to avoid this happening. And I suppose the meat of the guidance will be in Chapter 3, which is about the kind of retrofitting measures that are available and the kind of steps that need to be followed when you're developing a retrofit strategy and the kind of works you need to do before you even start. The kind of materials that are appropriate for retrofitting works on a traditional building, preparing and installing the different measures for the different elements of the building, so the roofs, floors, windows and doors, and the walls. Walls are probably the most problematic when it comes to upgrading a traditional building, has potentially problems there. And then we look at other non-fabric efficiency measures that might be, easy, low cost and easy to implement. Chapter 4 then we'll look at, dealing with existing heating systems, choosing new heating systems and what might be appropriate to the different types of buildings, how you might supplement the energy usage with renewable sources, accommodating changes. This can often be a problem. Locating plant, where does it go? What impacts would that have on the character of the building, or even just the structural capability of the building to support these. And then looking at management systems that help assess the environmental and energy performance of the building. Then we have a chapter on case studies. We may end up publishing these separately because things are moving on so quickly, but we look at a number of different building types, the kind of, the ones that come in to us most often looking for energy retrofitting works. And so these are largely hypothetical. They were typologies, to say, chosen to reflect the kind of most common traditional building types. And the aim was to look at, to improve them to BER B2 or as near as is practicable, as far as it's said technically, functionally and economically feasible. And some of these are going to be calculated then in accordance with NEEP or DEEP, depending which is appropriate. These followed the principle of minimal intervention as required by architectural conservation principles, particularly where some of these case studies were protected structures. And then just to mention some of the related initiatives that are going on at the moment. We have commissioned a study into the embodied carbon and life cycle assessment to do with the retrofit of traditional buildings. So looking at, what are the emissions over the lifespan of the building, keeping the building as it is, retrofitting it versus demolishing it and rebuilding it with a much higher energy efficient building. We're also looking to pilot a number of exemplar projects this year, working with OPW, with several of the local authorities and our own colleagues on the housing side of the department, and then other institutions as well. We're trying to establish, demonstrate, monitor and publish, as we say there, best practice case studies, so that people will know, somewhere you can look to see what has been achieved by other buildings, what might be possible for appropriate and sensitive retrofitting of these traditional buildings, and kind of road testing the forthcoming guidance. Oliver Cannan's going to talk to you about the SEAI research project, Fab Trads, looking at the hydrothermal properties of a range of traditional construction in Ireland. And we're hoping the findings will inform, the BER ratings and the BER assessment, so they'll be of use for making sure that our historic and traditional buildings are correctly assessed. And then there are many other issues out there that also need to be addressed. I suppose one of the most important of these is training and upskilling, so that we have the specifiers and the installers there to carry out these works. And also owners too need to know what their building is capable of, what pitfalls they should be looking for, and seek the best way forward for their particular building. Looking to see about developing grant schemes that are tailored to traditional buildings and their retrofitting. Looking at the kind of materials that are appropriate and making sure they're certified for use in the Irish market and on Irish buildings and in the Irish climate. And as I said, also looking at further studies into taking account of the embodied carbon that is in our existing historic building stock. So thank you very much. Very quick run through. Thank you.
Okay, hello everyone. I'm Oliver Cannan, and I'm going to introduce, as Jackie said, the Fab Trads project, which is testing the hydrothermal properties of the building materials that Jackie talked about that are common in traditional and historic building fabrics. Now really, I am just the lead applicant on this project and PI of the project at UCD, but it's very much a team project, and all credit to the team who are working on this. And they include Roseanne Walker, who's the research fellow on the project and is leading on the kind of the hydrothermal testing in the laboratory particularly. Anna Hofheinz, who's here in the crowd with us, is design fellow at the School of Architecture, Planning and Environmental Policy, practicing architect and doing a PhD, and is leading on the thermal evaluation of the materials. And Caroline Engel-Purcell, formerly of Carrick Conservation, is postdoc on the project and on the MacAir project, and is working primarily on the in situ testing of building fabrics. So the wall typology we're working with is this one here on the right as you look at it. Certainly not this one on the left, which is very common in the showrooms of the Energy Show behind us today, but rather this one, which is either rubble walls, solid stone walls, cut stone, solid brick, cob walls, the wide range and the wide dimensionality of building fabrics that exist in traditional and historic buildings. And these walls contain materials, stones from all over the country, very different types of stone, very different types of clay that were used to develop the range of bricks that we use in our buildings. So we're trying to gather and test as many of these as we can. And the major aim, as Jackie kind of outlined, is to try and correct for the lack, I suppose, of data that exists in our national methodology of calculation of our building rating. Essentially everything pre-1970s and particularly pre-1940s is given a default U value. So all solid walls or stone walls that contain stone are given a default U value of 2.1, often presumed to be on the high side, leading to people rushing to retrofit, and in often cases retrofitting incorrectly or inappropriately, maybe. Otherwise, the brick walls of 2.1 U value and 1.64 for 225 or 325 millimeter solid brick walls. So we're trying to fill this, this gap, I suppose, in knowledge. And I'll come back to this slide later in the presentation, but this is kind of the range or a sample set of the in situ U values that we've done to date for a wide range of fabrics. And this is very much Caroline's work. And we're not seeing a major, I suppose, trend in any way. We are seeing a lot of traditional walls coming in below the U values. But for those walls that are heavily saturated with moisture, we see them above the U values, the default U values as specified in DEEP. So it's very much dependent on the in situ conditions. But just to give you some examples of the work that we're doing, and I should have said at the start that this is a 3-year project. It was funded by the RD&D 2021 call and kicked off 10 months ago. So we're very much in the early stages of the project. So the results I show today are preliminary, and hopefully we'll be invited back next year or the year after to present a more comprehensive data set. So very much preliminary results today. But this is an example of a stone building built in 1740, traditional construction, including granite rubble wall with lime mortar or lime render on the inside, on the exterior. And in this building, we are doing in situ U value testing, and then we're taking samples from this property and bringing them back to the laboratory for a wider range of hygrothermal testing in UCD. This is an example of a wall at 480 millimeters width with a U value below, well below the default U value. Instead of 2.1, we're seeing a U value of 1.35. Another example of a building, in this case it's limestone rubble with a limestone facing and battens and a lath and plaster interior finish. Port Arlington Station and Irish Rail have been very good to supply us with a number of very good case studies. We're again seeing the U value of this building below the default U value of 2.1 at 1.9. So as I say, you know, we're aiming to try and gather a wide data set of these kind of typologies of buildings so that we can, I suppose, present a more nuanced list of stone or traditional building fabrics that can be used in DEEP. As I say, what we do then is we take a sample from the fabric, or samples from the fabric, bring them back in to the lab, core them to make these samples that we can then test for a wide range of hygrothermal properties. And those include a number of properties that the SEAI outlined in the call for us. Also properties that WFI have outlined for us, and WFI is the hydrothermal analysis software that will include this database of iris samples in their software in later iterations. So the sample set that we're developing will be available to building designers and analysers so that they can get an accurate picture of the materiality of Irish building fabrics. The tests that we're doing include thermal conductivity testing, which is a key test to try and understand heat transfer through the materials. The capillary absorption test, where we're essentially monitoring the uptake of water through the fabric, maybe a property relevant for driving rain or heavy surface moisture buildup. Vapor permeability, in contrast, measures the permeability of the material to vapor movement through the sample. And all of these are done to standards. In certain cases, we've had to just adapt to suit the materials, the nuances of traditional materials. And we've done this in conversation with WFI in many cases. Bulk density testing allows us to get the density of the material, but also the porosity of the material, which affects many of the other parameters. Moisture adsorption is essentially the uptake of moisture vapor, and we're testing that at a number of different relative humidities. The moment, the big investments we've made on two big multi-$1,000 climate chambers, both of them are causing us problems, so this test is stalled. So essentially, that's why we're presenting an incomplete data set today, is a hardware issue that we have. And then a much simpler test is free saturation, which is one that WUFI actually asked for, where we essentially dunk the materials in vats of water and then measure the uptake of moisture. So some quite complex tests, some very simple rudimentary tests. And just to, I suppose, present, as I say, very preliminary results to you, but maybe some contrasts that might be interesting. And I hope this is visible to everyone down the back. But say, if we the top of the two highlighted of these materials is the granite that exists in the WUFI database, measured by TU Dresden. That has a porosity of 9.5% per volume of material. When we did our tests on Carlow granite, taken from the house that I showed earlier, we got a porosity of 3% per volume. And hence, the thermal conductivity is, so that's the porosity value. The thermal conductivity value is higher because with less pores in it, it's more dense. More dense materials have a better ability to transmit heat. So we get a higher thermal conductivity. We get a lower water absorption coefficient. Again, less porous, less water absorption, and less free saturation. I hope I'm right in all those relationships. But that's one example of varying characteristics that we're seeing. Also, we're seeing quite a wide range of properties, even in the stone types that we're working with. So if we look at two different types of stone, one being the Laois blue limestone, the other being Portland stone, that a sample of which we got from the Customs House, a much younger stone, and that shows much greater porosity than actually the Laois blue limestone, much greater. And as a result, although not linear and quite strongly non-linear, we're seeing a water absorption coefficient that's much lower in the Laois limestone than in the Portland stone. And you'll also see that we're still waiting on other results to try and to complete this data set. We've tested a wide range of bricks. I think we've done 8 bricks at this stage. We're still searching for more, and I'll talk about that towards the end of the project. What we're seeing is generally a lower thermal conductivity than what's documented in the literature for the range of bricks that we have, primarily because the porosity is higher than the porosity of the bricks that are documented, particularly in the WUFI database. And as a result also, we are seeing a much higher free saturation level, so more likelihood of the Irish bricks taking up water than those that are documented in Central Europe. And this is why, really, like, we see a wide variety. This image down here on the bottom right are images of 4 different types of bricks, so slices from bricks, but all taken from the same wall. So you see the wide variability, even visually, in the bricks that we're testing. And as a result, these are B2, B7, B10, 3 different types of bricks. I think they're primarily yellow bricks. And what we see is a wide variability across those samples as a result. These are results for capillary absorption against time. So a much greater uptake of moisture as a result of the different capillary absorption parameters. Also, some maybe somewhat obvious kind of results, but we see thermal conductivity increase as the density of the brick increases and decreases as the porosity of the brick increases. So thermal conductivity on the y-axis, density and porosity on the x-axis for both images. And of course, the bricks having a lower density have a much lower thermal conductivity than the stones, which have a much higher density, much greater thermal conductivity. Similarly, the water diffusion resistance increases as the porosity decreases. Again, a result that I suppose is to be expected. But what we're going to do with all of these results is to try and bring them all together to create these data sheets, essentially, for as many bricks as we can test with the funding that we have, and develop these data sheets so that designers and building assessors can use these data sheets when they do their own analysis of their building fabrics, particularly building fabrics for retrofit. Because the aim is to develop this material data so that this material data, which will be available through WFI, will then be importable or selectable so that you'll be able to specify Irish bricks within WFI to undertake your moisture risk assessment. And here are just some very early results from WFI analysis that we've done, showing in this case the difference between results are the simulations using the Fab Trads range of parameters versus the WFI range of parameters. So I should just explain these graphics. The outside is on the left of each of these walls. These are sections through wall build-up. So in the top case, it's an uninsulated solid brick wall. In the bottom case, we've added insulation and render in both cases. And we are seeing some differences. I mean, all we can say at this stage is we are seeing some differences in moisture response using the Irish parameters to using the standard WFI parameters. We need to really complete the data set of parameters before we can draw any major recommendations from this analysis. But we have been playing around with different insulation types. So, looking, say, at the green in this case is the relative humidity, and the blue is the water content. The red is the temperature through the wall sections. So the top simulation, so the uninsulated brick wall is on the left. To the right of that is one that has been insulated brick wall that is insulated using EPS on the interior. And we see a very high relative humidity at the interface between the impermeable insulation and the brick front. Conditions that are, very risky of leading to mold growth with relative humidities of, somewhere between 85 and 90%. Simulating using a cork and lime render in this case, we see a much better moisture response that we'd like to see, where we see a kind of a downturn in the relative humidity close to that interface between the brick surface and the insulation layer. And we know it's not recommended standardly, in conservation practice, but we have been playing around as well with different water repellents on the surface of the brick. And the early results that we're seeing is that, the moisture uptake at the surface of the brick is much lower, relative humidity in the wall section much lower, and much less risk of moisture development within it. This is a multi-year simulation. So ignoring the early stage of the simulation and just looking at where the simulation stabilizes. Each line is the 1st of October, so that's the kind of the winter and summer kind of peak and trough cycle. 80% line there, the grey line that you might be able to see, corresponding to 80% RH risk threshold. So the EPS insulated wall, much higher than that. With very dangerous conditions for mold growth. Although we do see, retrofit solutions, permeable retrofit solutions also causing maybe some risks at certain times of the year, but then drying out as the weather warms. And then at the bottom we see the no insulation solution, which yet might be the most appropriate. I don't know, it's early days and it's not one that we're going to jump to, but what we see in that case is that there's much less risk of mold growth because there's much lower relative humidity values at that interface, dangerous interface between the brick surface and the insulation. I suppose from our perspective, what we are seeing is that we are seeing variability between the WFI simulation and the Fab Trads results, I suppose, giving us some faith that the the experimental routine is important and worthwhile. So just to finish again with a couple of samples, this is a solid brick property in Rathgar, kind of what might be understood as a solid brick wall, but really is two leaves of brick with a red brick on the external and a yellow brick on the internal, and header bricks every 7 rows. Again, coming in under U value at 1.58, and I suppose, you know, allowing us kind of all of this work related to the bricks will allow us build up a much more comprehensive and rich list of brick building envelopes, so that we can include them in the DEEP methodology. We have yet, I suppose, we've only done a few of our U-value tests have been done on brick fabrics, so we really can't conclude anything yet. But we are seeing a number of tests where the U values in situ are higher than the DEEP default values, and this is something, I suppose, a challenge of the project that we have, because it's very difficult for us in the in situ situation to control for moisture. In so many of these buildings, there is extensive moisture buildup when we do the tests, and in that case we are seeing the U values be higher than the default values. In those properties where the walls are drier, we often see the U values in situ lower than the DEEP U values, but this is something that we will report back on and conclude on at a much later stage in the project. So that's it. That's an overview of initial results and the project. I suppose to finish, I want to make a plea to people. Many of you might work in the field of conservation. Many of you might have access to buildings with a wide range of materials. Currently, we are very Dublin-centric. A lot of our materials have come from the Dublin region or the regions around. We have very little from the West. And we're very keen to build up a kind of a national database. So if you do have a building that is enclosed and heatable, we can do an in situ U value test there. But that building also needs to be going through some level of deconstruction, so that we can take samples from that building and bring them back into the laboratory. So if you meet those criteria, we'd love to talk to you, and we'd love to get some samples, and we'd love to come test your building or a building you might know of. Particularly, there's a couple that we're really missing from our database currently. We have no Georgian red brick, facing red brick. It's just not many Georgian buildings going through, I suppose, have their face deconstructed. So we're lacking that material. We're lacking cob buildings, particularly earthen buildings. We're lacking a number of sandstones. I think we particularly red sandstones. So do let us know if you have any of those, and I and the team are happy to answer any questions. Thank you.
So last one to speak now is Joseph Little.
Brilliant. Thank you for that, Brian. That was two fascinating talks there, both providing really much needed guidance. And I just think back on when I started this kind of journey around 2009, even 2008, when the home energy retrofit scheme was piloted, and how little we knew. I wrote at the time a series of articles called Breaking the Mold, which was kind of asking, do we know what we're doing? And we know a lot more about what we're doing now than we did then, I think. So interesting times. Just in terms of the hydrothermal concerns and moisture risk assessment and getting it right, it's nice to see, you know, UCD and TU Dublin working in parallel, because we teach the hydrothermal risk assessment module in the MSc in building performance. We teach it as a CPD, and we also teach it as part of the year one or the postgraduate certificate in that programme, which is grant aided. So if you want to understand those graphs that Oliver was showing you earlier on and those kind of concerns, you can come to us. for the learning as a building design professional, and then you can look at their report in terms of some of the values that we should use. I've been teaching that whole subject since 2010 in both the UK and Ireland. I'm the leading lecturer in both areas, trainer, lecturer. And one of the things I've tried to do, and even write papers around, is to help people navigate in a context where that kind of information that Oliver and his team are uncovering was not available. So what do you do? How do you make sober risk assessments when you don't have all the information? And it is possible to do that, to work in an accurate methodology, accepting that the precision is poor. But it's fantastic that we're close to getting more and more of this information. And of course, you could probably double or treble or quadruple the data set you're talking about, but it's a fantastic and very credible start. So, well done. Well done to the funders and well done to the people taking part. This is like a sorbet because this is going to have almost no figures, and it's all about action. It's all about judgment and building in work. It's a piddling, if you can say that in a public event, a piddling 38 square metre renovation. It's tiny, okay, but it has many of the thinking, hopefully embodied in it, that we need to see in much larger projects, and even perhaps in the national agenda of making very dramatic and very deep cuts in our carbon. I hope it's being said today elsewhere. It's not a very nice thing to dwell on, but we are in deep trouble. Planet Earth and the citizens of the human citizens, but also the rest of the plant life and animal life on the planet that depends on us to be somewhat sensible. We're in deep trouble, and we actually need to change radically the way we do things. And we don't really think about that enough. And I think Greta Thunberg's comment, you've no right to feel either despair or anything else unless you actually do something. And doing something is very empowering, it's very positive, it's exciting, it could be enriching. So that's my call to action, guys. Anyway, so in this little project, and it's extracted from a seminar that I gave on Friday, and it itself is an interim piece of work like Oliver's. There's more work to come behind this. There'll be a few scientific papers hopefully coming out of it. But we will have a recording from the talk that was given by several of us on Friday. Given time limits here, this is an extracted part of it without many of the figures. But life cycle assessment, building energy modelling, point cloud scanning, a whole range of discussions took part to aid the renovation works and to understand the impact of what we did. So these are the kind of the themes in black in the middle that we're going to look at now. So the first thing in terms of circularity, and that can have a massive impact on the embodied carbon of what we're doing right now, but also the access to materials in the future, where we cannot presume that the future will have easy access to many materials. We can't actually presume a future where steel beams, for instance, can simply be ordered, or that there is another quarry to provide aggregate for another concrete slab. We can't actually, and we shouldn't actually presume those things. We do need to think more and more about the circularity of the buildings that we make and how we can disassemble them, and those materials can go on further. And then that's for new build as well as retrofit. But then Jackie added something to that, saying if there is a moisture risk issue as well, we need to be able to, in some cases, remove those materials simply to be able to actually solve that issue. But that issue shouldn't happen in the first place if we design properly, build properly, and maintain properly. So in terms of circularity, the catchy reduce, reuse, recycle that my 10-year-old child comes back from school singing a song about, it's not just a jingle, it's actually a waste hierarchy. So, with so many things, we need to rethink what we're doing. Do we actually need that building? Could we go with have a smaller extension? Is the building inherently better quality than we understand? Is maintenance really what's needed first? The things that we don't do, the slab we don't build. I recently had the experience for a garden room in my own house, a different property to this one, where we were trying to put in screw piles for a garden room. And what stopped us putting in screw piles is that the government limit for height that meets an exemption in planning for a structure in a curtilage is 3 metres height. If they made it 3.5 metres height, you could have a nationwide campaign to encourage the use of screw piles for garden rooms that people are building everywhere throughout the country with no concrete, at all. And 18 screw piles get brought in under your shoulder, and each one costs €45. Like, that's possible if we could adjust by half a square metre the height of an exempted garden room. And think of that in terms of reusability, disassemblability, lower carbon structures, less, groundwater, lots of different conversations. So there are many, many things that we can do, that some of them are very small measures that can have a very big impact. There's obviously repairing, maintaining that building, repairing that building. using it better. There's reducing the amount of the thing that we need. There's reusing the thing that we do need, and we need to do an awful lot more of that reuse. And again, Jackie's comment and this whole engagement with existing buildings is about respecting them, understanding them, and reusing them, and continuing to gain that benefit, because all that carbon is locked in, that penalty has been paid, they're here now, and they're part of our patrimony, our streetscapes. They're the 90% of buildings will need to retrofit to carbon neutral by 2050, they're here now. So it's about honouring that properly and then doing the science that Oliver and co were showing you. And the last thing you should do, and what's beyond this is incineration for energy, and beyond that is landfill. Recycling is almost the worst thing you can do, but it's the one we like to talk about, and it has that cute little circular diagram. So recycling is great, but there are so many things we need to be doing before we get to recycling. We need to kind of almost demote the value we give to it. The other things above are far, far more important, okay, in a conversation about circularity and low embodied carbon. Now, a way of kind of conceptualizing that and looking at that in an international framework, and a way of looking at materials, is to start looking at what the what's her name, Ellen MacArthur, the Ellen MacArthur Foundation has done. They're leading the world in an engagement with circularity. And they talk about separating out the biomaterials, which is a flow of materials on the left side of the diagram, from the technical materials on the right-hand side of the diagram. And if you look on the table in front of me, the materials on the right are all, from your right, are all biomaterials, and they're mostly brown. And the materials on the left, and increasingly so the far left, are technical materials. And it's about understanding those differences and valuing both of them. I'll talk a little bit more about them later on. Valuing them both, but also separating them and recognising that if we want to recycle or reuse those materials better, it's far better to keep them separate, and it's also far better to keep them as close as possible to their current condition. The more you break them down, the more you recycle and break down to a glass sheet into glass cullet, or a glass bottle into glass cullet, or like almost a dust, or break down solid wood to wood fibre. The more you do that, the more energy is required to remake a new material, and you're into remanufacturing. So it's important that we try and use things as components rather than as products, and as products rather than as materials, and as materials rather than as recyclate. There's actually a hierarchy there, and if we can begin, our industry needs to mature in that regard and understand these things far better. Where are we in Ireland at the moment? Where are we in the conversation about circularity in the world? Certainly in Europe. We're just above Romania, guys. We beat the Romanians. But in terms of, let's say, the Latvians, we're twice as bad as the Latvians. And in terms of the Dutch, I don't know, are we 30 times worse? Somebody could do the maths on that one. Are we 30 or, actually, sorry, we're much worse than that there. No, we're talking about 20 times worse than the Dutch. Okay, so there is modern countries with very evolved economies doing great things, not too far from us, that have actively engaged both at policy level, practical level, and market level with circularity, what that can mean, and they do great things. This is not about killing a market, this is about re-engineering a market so that we can be somewhat sane and sustainable going forward. We've a long, long way to go. But that also makes clear that the low-hanging fruit, there's lots of low-hanging fruit. In the same way back in 1991, when we brought in the building regulations, we knew that in terms of reducing, improving our energy efficiency, reducing our energy usages, there was lots of low-hanging fruit in terms of just increase the boiler efficiency, or a few heating controls, or lag your cylinder, those sorts of conversations. They're all low-hanging fruit. In terms about energy and carbon, operational carbon, but in terms of embodied carbon and in terms of circularity, there is a lot of low-hanging fruits wide open for us before we need to engage further. The Dutch have a lot harder job now to go further than they are, but we need to get to where the Dutch are as soon as possible. So if we were talking about kind of strategies that would help us do that, you could talk about building less and then retrofitting first. So the embodied carbon of retrofit is about a third the embodied carbon of rebuilding. Okay, very simple rule. It's about a third, and I found that in my own projects as well as other sources. But of course, in building less, in retrofitting more, there's multiple other benefits in terms of streetscape, in terms of settled communities, in terms of the volume, the architectural quality. There's so many other benefits we can talk about. Why do we have buildings like this? Why don't we just put in place a glass box instead of the RDS? And all of you could come up with many reasons why the RDS is a beautiful thing, a useful thing, and let's not change it. So we can have the same conversations about lots of other buildings and in many ways. But we also need to use less building materials when we do some works. And in many cases, we need to refuse those works. You know, do we need, if you reduce your domestic extension or you reduce your commercial new build by 10%, you'd have a very significant impact on the cost of the building, but also its impact. However, you mightn't even notice the reduction in utility. If you look at Grand Designs is an intriguing programme on British television for many years that promotes the building of ground scrapers and horribly impactful buildings that are far, far bigger than the couples that ever use those buildings. I mean, we do, you know, and yet it's intriguing to watch, but it's a car crash in terms of sustainability, even when they use the so-called sustainable materials, simply often because of size and location. We need to maintain and repair more. We need to reduce materials used and structurally optimise. In this project, you'll see where the engineer wanted much larger slabs. We had conversations that were awkward, but they reduced the size of the slab. And in so doing, we reduced the impact. So very often, you know, there's that conversation too. And then there's also the specification of that. So do you need it in the first place? Do you need as much of it? Can you then improve the specification? And again, this is kind of like a hierarchy. So shifting the specification to low carbon materials, renewable materials, reused materials. Several of the materials on this table are reused materials, and I'll tell you more later in a kind of an extraordinary way. We need to transition supply chain from over-reliance on imported products and carbon-intensive native manufacturing to local, low-carbon construction product sector. And that's good news in terms of the economy. It's also good news in terms of carbon. It's good news in terms of innovation. But we have to do it anyway. Let's embrace it. And then in terms of circularity, we need to specify reuse and specify remanufacturing so much more often. We, as designers in this room, need to stimulate, and clients need to stimulate the market, and we need to design for disassembly because future generations need the materials we're using.